Hello everyone, welcome to the MATLAB tutorial of Medical Image Analysis course by Professor Ganapati Krishnamurthy. In today's tutorial, we will demonstrate three active contour based segmentation techniques discussed by the professor in the lecture videos. These techniques are active snakes, geodesic active contours, and Chan-Vese segmentation. Please carefully go through the lecture before this tutorial because we will focus only on the numerical method aspects and not on the theory. Okay, so we start with snakes. As professor discussed, the energy functional to be minimized for snakes consists of two parts. A. External energy or data term, and B. Internal energy or regularization term. The expression for the two terms are shown on your screen. Please note that C here represents the parameterized equation of snake. For example, the parameterized equation of a circle is shown on the right hand side. C vector is equal to x star and y star, and this is parameterized by S. Here the parameter S varies between 0 to 1. To find the optimum C, we have to solve Euler-Lagrange equation involving second order terms. Here is the formula for it. The value of J and F here in our case would be these. So on plugging these expressions, we get Euler-Lagrange equation as shown here. Now to find the snake evolution equation, that is step 3, we convert this problem into a pseudo-transient problem by introducing an unsteady term. So here is the unsteady term that we have introduced. And now we get the following equation, following unsteady equation. So when we do it, we get the following equation. Here, alpha and beta are the two parameters that determine the elastic and bending properties of snake, and here these parameters are function of S, but we assume that these are constants. So here one approximation comes into our first approximation comes into picture, and these equations get reduced to this one. So here alpha is alpha, beta is beta. Now this is the main snake evolution equation, and you can see it consists of 4 terms. So now we will discuss its numerical solution. Before that, please note that we are using x star y star to represent snake coordinates, and they are different from Cartesian coordinates xy, right? For example, here you can see the gradient in the 4th term here is taken with respect to snake coordinates and not Cartesian coordinates. Okay. Now when it comes to discretization, we will show discretization only for one component, but the second component will also be will be similar. So for example, we start with the unsteady term. So the unsteady term is approximated with the help of backward difference formula, which you can see here. xsj, here it is t minus 1, right? For simplification, in shorthand we can write xsj as xj. So xj at t minus xj at t minus 1 upon delta t. So this is the backward difference approximation of unsteady term. The second, and also you have to note that Now we come to the second and fourth derivatives, these two terms. The second and the fourth derivatives are calculated using central difference at present time. You see, we could have calculated this derivatives at t minus 1 as well, but we are calculating it at present time t. So this is common when we solve a partial differential equation using fully implicit methods. Then what we do, we calculate spatial derivatives at present time, right? So it looks like this is implicit kind of thing. Now we come to the last term. Although the second and fourth terms were computed at present time, like we do in implicit method, the fourth term is computed at past time, right? Like in explicit method, that is at t is equal to t minus 1. So because the fourth term is calculated at past time and the other terms are calculated at present time, so that is why it is called semi-implicit method, right? Okay. Now I explain the discretization of these terms. So given an image I, right, as a function of x and y, grad I can be found using Cartesian coordinates, and its magnitude, negative of its magnitude, gives external energy, right? Next, we take gradient of this energy and find its component along the snakes. Along the snakes is important, so we are trying to find its derivative, its gradient, with respect to x star at t minus 1, right? So the explicit term is here. So this is how we do it. So this is central difference only. Similarly we do for y. So when we substitute these values, we get a pentadiagonal matrix structure with coefficients as shown here: b, a plus 4b, 1 plus 2a plus 6b, right? Where the value of a and b is alpha delta t by delta s square, beta delta t by delta s to the power 4. Okay. So in matrix form, it reads mx star at t is equal to x star at t minus 1 plus delta t times del by del x star of e external at t minus 1, right? Here M is the cyclic pentadiagonal matrix, and we have to efficiently calculate its inverse to update the position of snake points. For example, you can see here, given x star t minus 1 and this del E by del x star, we can find x star t by this expression, but this involves calculation of M inverse. So because it is a pentadiagonal system, this we can use LU factorization to calculate its inverse efficiently. Okay. So in the lecture, this matrix M is same as A plus gamma times I. So this is just a change of notation, but it is the same as that. Okay. Okay, so now this is the basic snake algorithm that you will find at various places online. There are many advanced versions of snakes, but we are not going to discuss them here. In fact, in the MATLAB code that we will give to you, the code has some additional forces as well. For example, balloon forces as well as the gradient vector field forces. So there are many functions written for that purpose, right? Now we will show you some basic MATLAB, some MATLAB snippets to show that the basic structure taught in the class is present in the advanced code as well. For example, here is the code for calculating external forces, that is gradient of image. Note that here, so we can simply use gradient function in MATLAB and we can calculate energy. SQRT means a square root. Okay. So note that here fx fy, we got fx fy with the help of gradient, and this fx fy that we have got, it will be interpolated along the snake curves later. For example, here we have fx fy. Later we will use, like, we have to interpolate this fx and fy along xs and ys. These are the snake coordinates, you remember, because we had this del by del x star term, right? So we had to do that. Also, this is the code for pentadiagonal structure, and yeah, and this is the snake evolution equation. So thing is, there are many implementations of snakes that are available online. Our objective is just to tell you that you will find the basic steps that you learned in the class, that you will find them sitting even in the advanced codes. You will have some additional forces, your functional may be different, but these basic steps you will find there also. So when you look at a code, don't worry about it, because it may have some additional terms, no problem, but the basic structure will be there. You will be able to see a pentadiagonal system. You will be like seeing people calculate some external forces. Now, what is the external force? This depends on their energy functional, but it will be there. So you will be using some gradient, etc. So not a problem. So if you have, even if you have one code, one MATLAB code, you can like modify it to suit your purpose. Okay. So now we will show you an example of snakes in action. So for example, I run this code. So this code is not written by me. This is written by Mr. Kroon. It is available in MATLAB Central. Okay, so here you can see this is the initial contour, and you can see now this initial contour is moving, and slowly it is trying to fit this object, the boundaries of this object, right? Okay, so that is how these contours move. Here you can also see the external energy, and here is external force field. So because it is little bit slow, but you have already seen that you have an initial contour that is deforming in such a way that it fits the boundary. So it actually looks like this. Okay, so here you can see the top left figure shows the boundaries to be captured and the initial contour. The right left force, the right left figure shows you the magnitude of gradient of the image. Note that gradient is high near the edge, and this edge looks little bit diffused because it is convolved with a Gaussian filter, right? Now in the bottom left you see the image force vectors. So they are small, but you can magnify it. Maybe I will show you. So if you will magnify, so they are not very clear, but you can see you have image force vectors that actually pull the contour towards the edge, and their value is very high near the edge. As you move away from the edge, their length becomes very less, and after some times it becomes 0. For example, here it is all 0, here it is very less, near the edge it is little bit longer. Okay, also the bottom this. The bottom right figure shows the final position of the snake, and as you can see, the snake has fitted the object reasonably well. Hopefully so you can see here, now that is complete. So initially it was like this, now it has come to this position. So what we have seen is that the snake has fitted the object reasonably well. So we encourage you to play with various images, various initializations, right? Initialization means different initial control position, right? And you can also play with parameters alpha, beta, right? And there are some guidelines for the choice of alpha and beta. So typically a high value of alpha is used when like your image has deceptive image gradients, and the low value of beta is used for sharp edges. So this completes snakes, our first active contour model. So after this we come to the next model, which is geodesic active contours. So in snakes we were explicitly evolving the position of snake curve, like snake points, snake coordinates, by tracking position of its points, right? We had some points initially and we were tracking its position. So in this approach we use level sets. So in level set formulation, what we do, instead of moving the tracker points or contour points explicitly, right? We evolve a surface phi. Instead of evolving a curve C, right? Earlier we were evolving a curve, right? Curve C, but here in level set formulation we want to evolve a surface phi. Now the position of C is calculated implicitly, not directly. So how do we calculate it? So C is basically a set of points for which the value of phi is 0, or the set of points with 0 height. So for details I suggest you to revisit the lecture video by the professor. So and now I will be a little fast. So like in the case of snake, we will define an energy functional that attracts the contours of 0 height, that is C, towards the edges. So how do we do it? Given an image I, a simple edge indicator function is shown on your screen. It is small g. Right? We can use this function to determine the energy functional and then solve the Euler-Lagrange equation to arrive at the gradient descent equation. So this is our energy functional. Now it is written in terms of phi, not in terms of C. So it is here. Here delta is the smooth Dirac delta function, because right. So I have added timestamps also, right? So please go to these timestamps to understand more about the theory. I am just trying to explain you the mathematical formulation. Okay. So this is what we do. So we have this kind of driver force, the edge attractor. This is our energy functional, and when we solve Euler-Lagrange equation, we get this level set evolution equation. Okay. So in the MATLAB code shared with you, the idea is same, but the functional has some additional terms. Like in the case of snake, that code had some additional forces, balloon forces and gradient vector field forces. So here also it has some additional functional terms, in the functional, but don't worry about it. So I will show you that even though it looks complicated, the basic things that we have just seen are sitting there. So here are some snapshots for your reference. So for example, our initial phi, right? Initial level set is, suppose, a binary function. So if you have to represent this, you have to write like this, right? In MATLAB, you can write you can write a binary step function in this way. So its value is either -2 or +2. Then the edge indicator that we have seen, they have also used the same edge indicator. So this is how we write an edge indicator in MATLAB. Also here, please go to this almost at 25 minutes. Sir has explained that this is a smooth Dirac delta function. So for smooth Dirac delta function, sir has written 1 upon pi into epsilon upon epsilon square plus something, right? It was written like this, but here they have used some different formulation. So they are using this function to smooth it. You can use Sir's formula also, no problem. Then the level set evolution equation is, it has some additional terms, this alpha, this mu. So you can see this is the equation. So you can like maybe put lambda equal to 0, or some you can simply turn off some of the forces, and you will get a simpler model also, and you can check whether it is performing well or not, right? So this is the MATLAB code. Now we show you a sample implementation of this code. So let me show you. This is very slow. So you see, oh, it will take some time. So you see, the initial level set function was this, right? -2 + 2, the binary step function, and as after some time, after some iteration, because we are solving that unsteady equation, right? The shape of this initial level set function changes, and finally it becomes like this. And if you see, this is the 0 point, right? So when the height is 0, the contour at that point is the curve C. So if you see, the contour actually coincides with the boundaries of these two objects that we wanted to capture. And this is something that we cannot do easily with snakes, right? So you can see here we are not evolving the contour directly. Actually, we are evolving this phi function. So from this binary step function to this function, this is evolved in such a way that the contours come close to the edges, right? This. So there are various versions of level set methods for available online. You can check them. You can play with them. But our objective was to show the basic idea. Okay, so now I come to the last part, the last model. It is called Chan-Vese model. So this is also a level set based active contour model, but the difference is in the value of functional, right? So here, instead of using an edge attractor, the functional used is it is called Mumford-Shah functional, and it contains three terms: FA, FB, FC. So here, if f is an image, small f, and u is its piecewise smooth approximation, and c is an evolving curve in gamma, some computational domain, right? Then and also omega by c, omega over c represents domain inside c, right? So with this notation, the formula of Mumford-Shaw functional looks like this. Okay, so what it does is the first term fa, it penalizes. So if you have a long length, if the length of the contour, right, is long, it you will penalize. So its objective is to keep C smooth and compact, right? The third term FC, it penalizes for edges within segmented region. So for example, you have segmented some region with the help of a contour C. So within that region, if you have a lot of gradients, right? If you have a lot of gradients, that means there are some edges. So it penalizes if you have too many edges in the region. So right. So the objective is to avoid too many edges in the region bounded by the C. Now the second term FB, it looks like mean square error, right? So it penalizes if the piecewise approximation is very different from the original image. So this is the main feature of this functional, like lambda times f minus u square, the FB term. So sir has explained this in at 3 minutes in the lecture video, so I will just take the same example. So here you can see here you just look at this figure, this expression here, f minus u. So here u, what we have taken for u is here u is simply the average of image intensity in the segmented region. So for example, here we have C, this white curve, right? So within that we have omega 1, outside it is omega 2. So whatever is the average within omega 1, that is mu 1, right? And then we are calculating f minus mu 1. So considering all possible options, you can see that the value of this energy functional will drop to 0 only when the curve fits the actual boundary. So in this case, you can see the first f1 will be greater than 0, f2 will be close to 0, because in f2 everything is smooth, right? In this case, f1, because most of the area is black, so f1 is almost 0, but outside we have black and is gray, so f2 will be greater than 0. Here in this case, you see there is black and white in both region, omega 1 also, omega 2 also, so that is why it is also greater than 0. So it will be fitting well only when we have this type of structure, and this is what we want to do. So if you consider all possible cases in the position of curve, the fitting term is minimized only in the case when the curve is on the boundary of the object, right? So this explains this this functional, right? So just like in the last two approaches, once we have a functional, but this functional is written in terms of C, and we want to use level set formulation, so we need to find a way to write this functional in the form of phi, right? So in the level set formulation, given constraints on C, the energy functional in terms of phi can be written as follows, right? Here h is Heaviside function, so because it is not differentiable, its smooth version should be used. So please refer to this timestamp in the lecture to know what smooth version should we use. So once we have this functional in terms of phi, we can again use the same Euler-Lagrange equation and find the this gradient descent equation. So this is what we get: del phi by del t is equal to this Dirac delta times this function, right? So this is again because we want to use smooth functions, So this direct delta function is smoothed with the help of this function, 1 upon pi times epsilon upon phi square plus e square, right? So now I will like now, because this formulation is shown to you in the MATLAB snippet, we will show you the mean square loss term, right? This term that we were explaining for so long, how this is implemented in the Chan-Vese segmentation. So this code is by Sean Langton, and it is available in MATLAB. It is available in MATLAB Central. So in this snippet, you can see, like, with the help of level set, we can first find the interior points, then exterior points, and then we are calculating the mean of that, right? Mean of these points, right? U and V. So this is basically mu1 and mu2 in our expression here. The thing, this mu1, mu2. So we are calculating in MATLAB like this, and then this formula, the force from image information. So you see, I minus u square plus I minus v square. So this is same as this, right? F minus u. So you can see, and also, like, it has some other terms also, get curvature, etc. So that I do not know. So, but it has some more terms also. But like in the previous examples, we can see that whatever we have learned in this course is actually sitting in the advanced code also, and you can like play with parameters. Like you can modify the code, like simplify the code for your purpose also, or you can even make like add your own terms and see if the results improve or not. So you can play with this code, right? But the main thing is, whatever we are learning here is actually deployed in these models. So here is an example, an example of Chan-Vese of Chan-Vese segmentation. So you have an initial image of this aircraft. You initialize it with this. So this is your initial level set, and then after some iterations, you get this. So I will show you. So if you run this, you see, this is your input image. Yes, this is your initial level set, and after some time, you can see it is able to like capture the boundaries of this aircraft. Yeah. So thanks everyone.